So, welcome everybody in the audience to the UC Santa Cruz Center for Computational Experience's virtual panel. I'm Catherine Isbister, I'm the director of the center, and we're very excited to have you here for tonight's topic, which is data visualization. So before we get started, I wanted to say just a tiny bit about the center. We've been around UC Santa Cruz for about 10 years now, and we innovate technology practices and platforms to enhance everyday lived human experience. We draw upon the unique strengths and sensibilities of UC Santa Cruz, a deep concern for well-being and social good, closeness to and respect for the natural world, and technological skill, with Silicon Valley less than an hour away. The center's mission encompasses a broad range of computationally enabled activities, from VR stroke rehab to apps that help users track and manage mood, to wearables that assist conversational balance, to work like what you're going to see today at the intersection of data viz and other fields such as machine learning. I will paste the URL for the center into the chat so you can peruse our range of research projects and faculty in a moment. But before we dive into the program, just a few logistical notes. You can type questions into the text chat throughout the speaker's brief presentations. And after each speaker, we'll take some few questions. And we'll also have time at the end. We've allowed plenty of time for a general, hopefully lively discussion. And I will be making sure we cover all the questions. My center administrator, Jonathan Morales-Rocha, will help with that too. Okay, so let me just quickly paste this link in here in case you want to look at the work we do. And now let's get started. So our first panelist is Angus Forbes. Angus is an associate professor in UC Santa Cruz's Computational Media Department, where he directs the Creative Coding Lab. His research investigates novel techniques for visualizing and interacting with complex scientific information. He's a leader in his field at the intersection of data visualization and aesthetics. He'll be giving us a brief overview of his lab's work today and of how he thinks about the area of data visualization. So take it away, Angus.
Thank you, Catherine. Give me 1 second to share my screen. Nope, I hit the wrong button. That's the button I'm looking for. Can you see that? Okay, great. So nice to see everyone virtually. I wanted to start this talk today by giving a brief overview of some trends in data visualization and highlight the focus of some of the visualization research at the UC Santa Cruz Creative Coding Lab. And then Oskar and Sarah, the other panelists, will talk in more detail about some of their individual projects. So at the Creative Coding Lab, a part of our research is to develop novel ways to represent and analyze complex data sets and especially dynamic networks. We very often collaborate with scientists and researchers to design visualization tools that make it easier for them to reason about their own data. In the past, we've worked with systems biologists, material scientists, neuroscientists, linguists, and astrophysicists to create specialized visual analysis tools. I think there's an enormous and really an essential opportunity for viz researchers and data scientists to collaborate with the wide range of scientists and researchers who work on big data to develop better ways to understand this immense amount of data that inundates our contemporary lives. And just very briefly, I'm going to show you a few screenshots of some of the visualization projects developed by our labs over the last year or two. The screenshot you're seeing now is developed in collaboration with systems biologists at Harvard Medical School. This is a tool called Dynamic Influence Networks. We came up with a novel way to represent rules that govern how proteins interact with each other inside a cell, a single cell. And this visualization shows how the presence of certain proteins makes it either more or less likely for other interactions to occur within the cell. This is a screenshot of a collaboration developed by our lab and by clinical neuroscientists at University of Illinois, Chicago. This project is called NeuroCave. It's an interactive VR project that lets the neuroscientists step inside their data in order to see patterns of brain activity in patients in response to different stimuli and different cognitive tasks. We also have a newer version of this that works with temporal MRI data sets. We've had a very successful collaboration with a team of astrophysicists at UC Santa Cruz and New Mexico State University. This is a project we developed last year called IGM-Viz for Intergalactic Medium Visualization, where we are integrating two different cosmological data sets to help with the analysis of this intergalactic media. One data set shows the location of different galaxies in the universe, and the other data set provides spectroscopic readings taken from the Hubble Space Telescope and other space telescopes that help astrophysicists reason about the makeup of the intergalactic gases that surround those galaxies. And this is a screenshot from a new project that we're still working on called CosmoViz, where we can visualize much, much larger data sets than in the previous project. We provide interactive rendering that shows the location and the structure of the dark matter filaments that make up the cosmic web in the universe. And one of the other speakers, Oskar, will be introducing some other of the visualization projects we've been working on later in this discussion. So data visualization is used for different purposes. And broadly speaking, I've broken them down to 4 different kind of areas. The first is to communicate ideas, usually to communicate an idea or an interpretation that's already been worked out or established, and you're using the data visualization, whether static or interactive, to let the reader or the user understand how you came up with that interpretation. Sometimes this is called infographics. You see this a lot in interactive journalism or data journalism. The second area, broadly speaking, might be called scientific visualization, and it's used to represent the salient part of complex systems, to highlight what the core operations are in some system that's been measured empirically. Data visualization is often used to explore data and to find relationships within or across different data sets in order to enable a user to come up with their own interpretations of the data. And in this case, the idea is the visualization is kind of minimalistic and neutral so that the user is able to make their own interpretations as easily as possible. And this is called information visualization, broadly speaking. And there's also an area of data visualization called visual analytics, where you build new models that use the data to make new inferences or new predictions from the data. And for all of these areas, they have something in common. The visualization serves as an interface between the raw information and the construction of meaning about that information. So again, visualization can be used when the data is already well understood. There's already a point to get across, and you use the visualization to emphasize, promote, or explain particular aspects of the data in order to support a particular point or interpretations. You may have heard of software tools like Tableau, which are often used for business graphics or for geographical representations. And there's also web libraries. You may have heard of a JavaScript library called D3, or there's libraries like Vega, which make it easy to customize your own information representations. And there are some great books by well-known visualization designers like Edward Tufte or Alberto Cairo. Isabel Moraes has a wonderful book called Design for Information. And going back a few decades, Jacques Bertin has a great book called Semiology of Graphics, which all provide helpful design principles for designing information. Viz researchers are often interested in coming up with new approaches to portray and to navigate data. So a lot of the research in the visualization field is thinking about these new portrayals or representations. And a lot of the research in this area is related specifically to understanding how we perceive and interpret different visual encodings or different visualization representations. And the practice of visualization design is in finding perceptually salient visual representations that make it easier for a user to interpret the data or to make sense of the data. And I'm just showing a screen, images of the covers of 2 books that I like a lot. There's a great textbook by Colin Ware called Information Visualization, Perception for Design. Another great book by Tamara Munzner called Visualization, Design, and Analysis. And these books discuss the relationship between representation, perception, and cognition. Another situation where you can use visualization is to simulate data, or in making inferences or predictions about your data. such as imagining the likely state of a system at a future date, or to interpolate reasonable data between the data samples that you've already collected. And again, Oskar Elek, who will be speaking later, is going to talk about a data reconstruction method that infers the structure of the cosmic web from a relatively sparse set of empirical observations. A lot of the most interesting visualization work we do relates to working with researchers on new types of data, or thinking of ways to make it possible to explore data sets in new ways. So new interaction motifs or new representation motifs. And this is because there are many processes that don't yet have best practices for how they should be modeled. And there's many types of data for which there's no best practices that define how they could be represented to make it more easily to assimilate the information. And interesting data sets that we as a lab come across in our collaborations a lot are often very complicated, very large, and they can contain data that's temporal, heterogeneous, ephemeral, multidimensional, probabilistic. And these types of data often require new approaches in order to represent them so that you can reason about them effectively. I think there's an inherent creativity to the data visualization process in terms of thinking about how to come up with new representations and new interactions, and in terms of taking advantage of new technologies, including new forms of interaction and immersion, whether it's VR or mobile devices or holographs or whatever else it might be. There's always new tools that data visualization researchers can use, hopefully to promote better understanding of data. Our lab also encourages artistic production. Some of our researchers are also artists or painters or computational media artists. And I have the expectation as a lab that effective design can emerge precisely at this intersection of focused problem solving and artistic exploration. That is, that creative explorations can inspire, potentially, effective ways to represent data. Sarah Frost will be speaking later within this hour and giving an overview of an interactive recommender system that she created, which helps a user make sense of a deep learning model that classifies artworks. So an exciting thing about visualization research is that there will always be more data. We continue to collect and store ever increasing amounts of data with higher and higher spatial and temporal resolutions. And moreover, I think, there will always be new types of data that don't have an obvious representation. New sensors are being built, new analysis methods are being created. And so even while our understanding of what visualization techniques are most effective continues to grow, there will always be new ways to interpret and analyze new types of data. And I guess the last point I want to make is that user-centered design often includes this ideation phase prior to the building of an artifact or a tool. And I think that the act of creating and not just using a data visualization is in and of itself a good way to understand a data set, as well as a good way to refine initial analysis tasks. This process of creating a data visualization can sometimes help us to figure out which analysis tasks are in fact the most meaningful to the researchers or to the user. So visualization serves as a way to mediate complexity as an interface that can help transform raw information into meaning. And there's various ways to do this. And you'll hear from our other speakers of some individual projects where they're able to take the raw data and create some very interesting interpretations that are useful for science and also for society. If you're curious about the lab, maybe Jonathan or Catherine wants to post this. I've got a link to my lab's website, the creative coding site. You can see a bunch of different projects. And feel welcome to reach out to me if you have any questions or to ask questions here in the chat. Thank you.
That was great. So just to remind the attendees, if you want, you can post a question in the Q&A. And I have one question for Angus, which is, it's always fun in these panels to hear like what's most exciting that's going on for you lately in your lab, you know, and anything else you feel like sharing of where your directions are going in the near future. Oh, you're muted, I think.
Goes with the territory. We have a few
it's top
different
secret. Sorry.
We have a few projects ongoing that are pretty interesting. On the creative side, I've been collaborating with a jazz drummer named George Marsh, who's at the music department at UC Santa Cruz. He has this very interesting way of notating music and rhythms in particular, and we're creating an animated visualization of this notation. On the research side, our lab does visualization, but also work in machine learning. My PhD student, Manu Thomas, has been working on a deep learning project which helps to improve and speed up graphics rendering. And I'm also very excited, as you probably could tell from the slides, about the visualization tools we've been creating in collaboration with the astrophysicists. We have, in addition to the two I showed, Oscar's going to talk about one, and we have a couple of others. So to me, being able to understand, get some insight into the structure of the universe we live in is awe-inspiring. So.
Absolutely, and drumming too, both important topics. Okay, well, people are shy and saving their questions for the general panel, so I'm going to go ahead and move on to our next panelist. So I did to introduce Oskar Elek, and he's a postdoctoral researcher in Angus's lab. Since his doctoral research at Max Planck Institute for Informatics in Germany and Charles University in Prague, Oskar's covered diverse topics in visual computing, from simulation of light transport to optics of participating media, appearance modeling, and computational fabrication. And his current work explores the intersection of nature-inspired simulation and visualization, and that's what he's going to be talking about tonight. So take it away, Oskar.
Thank you very much, Catherine. Let me share my screen. Right, all good? Okay, hope so.
Yes.
So this is work with Angus and also with Joe Burchett and Xavier Prochaska, who are astronomers at UCSC. And this abbreviation here, MCPM, this is a technical term. It means a Monte Carlo Fizerum machine, but really what I'm going to talk to you about is a bio-inspired reconstruction and visualization of the cosmic web. Let me start with a little metaphor. So imagine that you find yourself in a place that you don't know what it is. You just see fruit trees. So you're kind of in the middle of things, and you really can't tell much more. Now, if you actually step away from the place, you realize that there is kind of a hidden order to things, and that you're in an orchard. So the metaphor for the visualization that I want to start with is that visualization is not just about an abstraction for me. It's mainly a process of providing new perspectives into data through a process of reinterpretation. So this metaphor building is basically that. And with that, I'll start about the actual topic, which is visualization of the cosmic web. So most of you will be probably aware, cosmic web is the largest known structure in astronomy and astrophysics. It is literally a web of gas and dark matter that connects entire galaxies and galactic clusters together. So this is a picture that was produced in 2005 by the Millennium Simulation. And you can kind of see just how vast this structure is, because here individual galaxies are just single bright pixels, or maybe a few bright pixels across. So this is a really huge structure, much bigger than galaxies or anything else that we really know in the universe. Now, visually, when you look at this image, I don't know about you, but when I saw it for the first time, I was really, in awe. What it reminded me of was fractals. So I really deeply respect the work of Benoit Mandelbrot, the fractalist, as he called himself, and other people, who sort of brought fractals and just their ubiquity in nature to our public view or consciousness. And his work just reaches very far in different domains, although he was a mathematician and he actually described kind of more abstract of fractals. But yeah, when you see this image, it kind of pops up that this is a fractal, and it can be approached that way. Now, when you look in the universe, this is a Hubble deep field image. We don't see the cosmic web. And the reason is that because it's very faint, it's very diffuse medium, and in the case of dark matter, we really can't even observe it at all so far directly. So the story of this project actually started with Joe Burchett, who last year approached us and talked about the data that he would be interested in visualizing and gaining some insights into. This is an eagle simulation. So it's a cosmological simulation which actually puts together all the understanding about physics that we have and tries to come up with mini copies of our own universe that we can use to understand the real universe with. So when I saw this data, immediately this picture of the cosmic web and the fractal image kind of came back, and that kind of stayed. Now, a couple of months later, Angus sent me a post from a digital artist named Say Jensen, who's based in Berlin. And Say Jensen used the simulation of an organism called slime mold, here it is, to create these really interesting visual representations, these animations. This is what they look like, for instance. So you have a simulation of an organism running in real time, although it's a bit choppy now, and just kind of creating interesting visual artifacts that can inspire, and indeed they inspired us to actually look at the cosmic web from the perspective of these structures, and maybe even try to use them to visualize the cosmic web. So slime mold, if you don't know, is a unicellular organism of the protist class or family. It's a yellow blob that actually grows on trees in the forest. You can find it in California and elsewhere. And it creates these beautiful networks connecting food sources together. And what's remarkable about this organism is that it doesn't have any brain, and yet it basically solves interesting optimization problems, which has been used by people like Andrew Adamansky to actually use slime mold as kind of a computer to solve spatial problems, for instance, traveling salesman or optimal navigation. And that's actually what we did with it too, except that we didn't use the real organism. We used the virtual adaptation of it. So here is my friend who saw the post on Twitter and developed kind of a simple 3D demo of how the slime mold might grow in 3D. Apologies again for the choppiness of this. And when he approached me with this, I immediately thought, why don't we use this to reconstruct and visualize the cosmic web? So months later, this is what we had. The red spots are data. They are individual galaxies from this longitudinal digital sky survey. And you see the algorithm actually in real time feeding to this data, navigating through the virtual space and actually reconstructing the cosmic web. And when I fast forward a little bit more, you see kind of a converged image. So this visualization and reconstruction together, they're in real time, or they run in real time, and they take about a minute or two to actually get you this map. And the astronomers find this extremely useful, not only to get insights, but also to actually extract the data and create virtual maps of the cosmic web. So here you see details of this map, where these yellow blobs are individual galaxies in space, and the purple traces are actually the virtual slime mold growing over them. And what we found is that not only this is a very nicely fitting representation, but also it actually really captures the dynamics of the cosmic web. And so there really seems to be a deeper connection that we don't entirely understand yet, but fitting to real data and actually validating with measurements. In this paper, we were able to show that really there is something to this, and that something is quantifiable. Through visualization, we were also able to show different regions of the cosmic web. So for instance, here is kind of a density profile that we got out of the reconstruction process. And with visualization, you can really show that region in the density kind of space correspond to specific regions in this map, in the cosmic web map. For instance, here we're highlighting outskirts of the filaments, which are kind of just on the edge of galaxies, and kind of transiting into the open intergalactic space. Here is another paper that we published very recently, which actually probes the cosmic web between us, which would be on the left here, and an event called fast radio burst that would be originating here on the right. So this is about, this is very far. It's redshift 0.1, which translates to millions of light years away. But the whole point of this study was to visualize the cosmic web between us and the origin of the event. And actually, we shown what astronomers saw in the data, that the sight line, this red line, passes through a very dense region of the cosmic web, which you can see here from kind of the front view. And that really, the measurements they get from this fast radio burst are heavily influenced by the presence of the cosmic web. And our software helped them visualize the entire configuration. The software itself is called Polyform. Here you see it written 90 degrees rotated left. Polyform contains several visualization modalities that basically show different aspects of the cosmic web. Most of them are based on volume rendering, where we take the density field, the map reconstructed by the slime mold, and turn it through different coloring schemes into these informational views. You can slice the density field to get better insights into specific locations, can highlight different regions in the data to show these different density regimes that astronomers are interested in. So I definitely encourage you to download the software and play with it. It's open source. I'll show the link later. The reconstruction also allowed us to actually show different ways to kind of probe the cosmic web for other information. So these are just a few visualizations that we developed in collaboration with the astronomers that we presented recently at the VisAstro Data Challenge, and which won us the first place there for just the insights into this data. So let me conclude by saying that none of this would really happen without visualization, because just seeing these data in the new light enabled us to see this connection between the slime mold and the cosmic web, and eventually come to a working solution. The other thing is that simulation and visualization, when running together, are very powerful, just because you can actually change the simulation in real time and get an immediate feedback from the visualization and see get insights into the problem that you're solving. And finally, I'll just say aesthetics matter. So all this visual presentation is really developed with not only just being informative, but also being beautiful, because I think that inspires further work and inquiry into the topic. That's all from me. Thanks for your attention.
That was fantastic. Thanks, Oskar. So I noticed that Angus posted into the chat for anybody who's interested the Polyform GitHub link. So you made a provocative point at the end there, Oskar, about the importance of aesthetics. So can you tell us a little bit more about that? Or like, where do you think that comes into thinking about these tools and these kinds of visualizations?
I think it's very specific to every individual case, and I really like the idea of aesthetics just corresponding to the process somehow that leads to the visualization, or that guides the visualization. So in our case, let me see. So this is one visualization which is actually simulating light transport in this data. So we take this reconstruction provided by the algorithm and then render it as if it was a real physical object that transmits light, and actually the galaxies in this data set are sources of light, of illumination. Mm-hmm. And the aesthetic choices here are about colors. So the entire data set is a density field, right? So how do you actually draw this on a 2D screen is a challenge by itself. But because it is a 3D structure, you can't really rely on geometric kind of aids in the visualization itself. So what I use is just good choices of color that contrast with each other and essentially create this feeling that you really are in the space with this data as if they were a physical object. So I don't know if I achieved that, but hopefully there is something in there. The other aspect of this is kind of underlining the biological inspiration of the whole method. So for instance, here is work on word embeddings, which are kind of abstract spaces in linguistics. And we actually fitted the same algorithm to this abstract data, which we really don't have a very good idea what's in there structurally, but they're kind of used to find similar words to any given word. So for instance, here the blue word was research, and now you get all these results showing what kind of research there might be in this process data set. And here's a rendering using this slime mold to actually show this as kind of a biological entity, I guess, to just underline that language by itself is alive, and the way how it evolves is also organic. You know, how individual words or entire languages and dialects evolve is a continuous ongoing process, which really is as if the language was alive for me.
Wow, it's like the microbiome of conversation or something. That's amazing.
Exactly, yeah, that's the idea.
Very cool. Our attendees are being shy. Don't forget to type questions in if you have questions. Oh, here's one. Are there any efforts to visualize these cosmic threads physically through 3D printing or some other method?
That's an excellent question. We are working on it, in fact. So here is one illustration, which is not the astronomical data, but is more like a biological scaffolding, kind of like bone marrow. And we definitely want to 3D print this.
Wow.
3D printing the map itself, the cosmic web map, is a bit more tricky because the density distribution has pretty high dynamic range, like 4 or 5 orders of magnitude. So you actually have to do some processing to get this into a 3D printer, but it's an excellent idea. And we actually want to make a sculpture out of the slime mold data set and 3D print it and put it, actually gave it as a present to one of the department heads here at UCSC.
That
So stay tuned.
Yeah. Wonderful. Okay. That was a super presentation. Thanks so much. So we're going to go on to our final panelist, Sarah Frost. Sarah recently graduated from UC Santa Cruz with her master's in computational media, and she's interested in digital experiences and the use of emerging technological settings. She's worked with the Smithsonian's National Museum of the American Indian, with Google Arts and Culture, and the Orange County Museum of Art. And as Angus mentioned earlier, tonight she'll be speaking to us about visualizing emotion in art. So take it away, Sarah.
Thanks. Okay, does this appear to everyone? My screen appears?
Yep.
Great, fantastic. So like Catherine said, my name is Sarah Frost. I'm a recent graduate of the Computational Media Department. And tonight I'm going to talk to you about an ongoing research project that I'm working on and a visualization tool that I built. So what do you think of when you think of a traditional art experience, a traditional interaction with art? You probably think about walking around a room in a gallery or museum and looking at pieces of art on a wall. And how is that art organized? Could be organized by style, by genre, maybe by painter or time period. But what if we could visualize and organize art by the emotional impact of the art, by the way that it makes us feel, really sad or happy and positive? So this project that I'm going to talk to you about is motivated by the desire to apply data visualization techniques to enable novel emotion-based interactions with art, and specifically digital interactions, because more and more people are interacting with content and art content specifically on the web. So first, to talk about our data set, what we started with about 4,000 images of art that had been annotated by individuals with words representing the emotions evoked by the painting. So for example, this is an image in our data set, boy restraining a dog. And then on the right, you see the words that the painting evokes in the minds of the annotators. So we take these emotional words and we process them using a sentiment analysis tool called Luke, and we end up with an affect vector. This affect vector is a series of numbers, 5 numbers. Each number represents a score or value, 0 to 100, that shows the resonance or the amount of each emotion: happiness, anxiety, anger, sadness, and love in the painting. So this is the affect vector for boy restraining a dog. And once we do all of that processing for all the images in our database, we are left with this beautiful Excel spreadsheet, and that is the visualization of our data. Except it's not. This is not a good visualization at all. So I'm going to show you the next step, the 3 interactive visualizations that we built. So it's online at artifact.tech. So this first visualization method is we call sliders, our slider method. And you can see that each slider represents the value of one emotion. So anger, anxiety, happiness, sadness, and love. The user can move the slider, and then our lookup process runs, and the closest image to the slider values in our data set is retrieved. Next, this is our gradient visualization method. And so this, carousel. This is the carousel. So this visualization consists of 5 carousels that presents a more guided experience through our database of art. So on this page, the user is presented with 5 carousels that showcase the 15 artworks each that have the highest affect vectors. So for each emotion. And finally, this is our gradient visualization method. So this is a progression illustrating the movement, the exploration between 2 images, 2 anchor images. One is on the left and one is on the right. So this allows the user to explore the affect space between two existing paintings, and then to choose to see a painting that is more emotionally similar to the piece of art on the right or left. So in terms of next steps, where this project is going, we're hoping to collect more emotional data from users and expand our data set. Then we hope to train a neural network to predict the emotional affect from art that has not been annotated by users, so has not been seen by the machine or by people before. And then we hope to move into art manipulation and style transfer. So for instance, what would a more anxious Mona Lisa painting look like? And that's it. Thank you so much.
That was great. So we have a question from Lauren. She says, who are the annotators and how many evaluated each piece and how are they chosen? So where does this data set come from?
Great question. So this data set comes from researchers in Canada Saif Mohammed and Svetlana Kurchenko, and they compiled this data set, and they used crowdsourced workers, I think specifically from Mechanical Turk, to annotate the data set. Each piece of art was annotated by 10 people, and we had on average about 57 emotion words for each piece of art.
And then somebody else was asking about Luke, what Luke was.
Also a great question. Luke is a text analysis tool developed at UT Austin. So we feed in our emotion words and we get back that affect vector. We use that to standardize the sentiments and then transform the words from the crowd workers into that affect vector.
Nice. Let me think. I guess another question for you, I'm just curious, in playing with your own tools, is there any like really surprising thing that has happened in the course of building this, like an unexpected and surprising result for you that you would want to share?
I wasn't very surprised by this, but it was really rewarding to see how different painters across decades and centuries and different genres and all over the world represented the same emotions, and really created those very base universal emotions in the minds of the viewers in such different ways. So I guess to see that universality of emotion visualized was very cool.
Yeah, the tech changes, but the human equipment stays for the most part. All right, so those were all our presentations. If you have any kind of broader questions for these folks about data visualization, also have a lot of experience looking at the intersection of data viz and machine learning, which I know is a hot topic for many. In the meantime, I'm going to ask a couple of questions to kick things off. So question that has been in the minds of a lot of people with big data lately. Oh, actually, look at this. We have a couple questions. Let's start with these. So first question, how can you get trained in data viz?
Come to the Creative Coding Lab.
Yeah, I can take a stab at that. Many computer science departments or computational media departments will offer to data visualization. I know it does as well. Sometimes universities will have someone, I see someone says they're a sociologist, will use tools that are less programming intensive to try and visualize data. I do think it's useful to know some programming in order to create data visualizations, especially if they're meant to be interactive, or if there's some data pre-processing that needs to take shape in order to get it into the system so you can interact with it in the first place. You can also, there's lots of books out there about D3 or processing or matplotlib, or there's a language called R, which support visualization in various ways. So there's lots of ways to get into it. Most of the tools, this follow-up question is, are they free to access? Most of these tools are free to access. They're all tools like Tableau, which are sold to companies and require training, but the programming tools are generally open source and freely available, and the communities are usually very warm and inviting and want to share knowledge and love it when new people come in, especially if they have interesting questions from different perspectives, maybe from sociological perspectives. So I think there's lots of ways, and feel welcome to email me if you want to get some more information.
Yeah, you could probably share those those book recommendations too.
Right. Yeah, those book recommendations are great.
Angus. Yeah, and Phil had a question specifically for Sarah, I think, which is, could you imagine using your data set now to feed a machine learning algorithm to see how the AI tags pieces of art?
Yes, we can definitely imagine that. That is the goal. We have started to develop machine learning models, but we are constrained by the amount of data that we have. So 4,000 images might seem like a lot, but it's really not when we have such a complex problem. How do you teach a machine learning model what happiness looks like in a painting, or what is sadness? So that is is why we are trying to expand our data set, and then hopefully we will be able to do that very soon.
All right, so here's my big think question for the panelists, which is people have started to get really concerned with big data, but especially like the intersection of machine learning and big data with questions of ethics. So have you come across any ethical quandaries in doing your work? And if so, what were they and how did you work through them?
So anyone else want to take a stab at that?
Yeah. So with this particular, thinking about who decides what, I think the problem often with ethics and machine learning is the nature of the data set and the data that is being used to train the machine learning model. So if that's biased or if that's skewed in a way, then that will have an effect down the line. And so when I think about the type of art that we are representing and the fact that not all types of art are being represented in our data set currently, and how we're leaving out cultures and groups of people by doing that, as well as the fact that only 10 people have annotated each piece of art that we're using. I definitely think we're trying to rectify that moving forward. So I think in general, it's good to be aware of this and to hold each other accountable. I think we're really good at doing that in the computational media department, of asking those difficult questions before they have really negative impacts.
And just to follow up quickly, there's a tendency that if you see something represented, that it means it's true. And there needs to be kind of a broader visual literacy where we understand that any representation is inherently choices about what is including and what's not being included, as Sarah alluded to. But I also think that visualization and can be used to emphasize those probabilities or those uncertainties or those gaps. And so that to me is an exciting area of visualization research, where it's not just representing the data, but it's also being used to interrogate or question the boundaries of that data. Yes.
Yeah, so Phil says, in fact, one of the books you showed had truthfulness or something like that in the name, didn't it?
Yeah, that's a book by Alberto Cairo, who writes a lot about infographics and data journalism, and specifically tries to kind of point out that the graphics seem truthful, but actually you can lie with visualization, just like statistics, and to try to inspire people to be more critical, even when they're representing their data.
So one more broad question, which is, how do you see your work relating to how everyday people interact with data visualizations? So where would you most like to see what you do applied? So not everybody here is an astrophysicist or necessarily interested in art. Like, are there ways you could see what you're doing apply to everyday application spaces?
I'll answer that first in one direction, which is, although a lot of the work we do is research, we try and get funding from the National Science Foundation. We're trying to train grad students to become expert computational mediaists. But a lot of the people in computational media, a lot of the students and faculty are kind of hybrid thinkers and have a creative practice. So I personally like to get our work out, not just to computer science conferences, but also to art venues, museums, and galleries. And in fact, some of the students recently submitted work to the Museum of Art and History here in Santa Cruz, and their data visualization work will be shown in a museum setting. Nice. I also,
Very cool.
And the last thing I'll say about this is, although the starting place for a lot of the visualizations, especially things like working with astrophysicists or natural language processing experts, the initial goal is to make tools that help even the experts understand their own data. But the other side of data visualization is this communication aspect. And so a lot of times the follow-up to kind of the more esoteric, quote unquote, work is to use it as a communication tool to expose some of this thinking about new types of data to the general public.
I remember I saw Laurie Anderson give one of her performances, and she talked about how she did an artist residency at NASA, and she met the guy that colorized all the pictures from all of the telescopes and instruments, and she had never realized until then that that particular person was choosing the pink or the yellow or the blue. It kind of speaks back to Oscar's comment about aesthetics, but that, you know, how powerful those visualizations are for inspiring us about space, right? Yeah. So I think there was one more question from the audience. I want to make sure I circle back, which was, what challenges do you face in accessing and cleaning data for data visualization?
I mean, data scientists will tell you that, you know, you have this iceberg, right? On the very top is your beautiful analysis and your beautiful visualizations, but the rest of the iceberg is the data. Even if it's collected very assiduously and ethically, it's always kind of messy, and you never quite want to do with the data what it was. The way the data was organized never quite fits with what you want to do with it. So there's always a process of translating it or cleaning it or finding outliers in it. So I'm not sure exactly what the question is. How do we approach it? It's just you have to realize when you're working with big data sets or interesting data sets, especially new data sets where it might be collected by one instrument or one individual person, that there's always a process of I don't want to say reshaping, it sounds like you're manipulating the data, but transforming the data into a form where it's usable by you. Well,
this was the sociologists, and they actually used that term. Like, I was trained in social science too, and of cleaning data. Like, there must be some just crazy sensor error outlier points that end up in this data. So surely that must be a process too, is figuring out, or do they sort of clean it ahead of time, or does that end up being a part of the visualization process, is noticing funky things? And
I mean, I'd like to think of data visualization as an ongoing iterative process, and the fact of just the act of creating the data visualization often highlights the noise in the data sets or errors in the data set. So sometimes by visualizing the data, then you realize where the bias is, or whether the noise is, where the columns that were entered incorrectly are. So actually visualization, I think, goes hand in hand oftentimes with cleaning.
Yeah, it's like a living process. So the same person is saying, sometimes it's guided by curiosity, what research questions you have. Yeah, which is cool about how you're working so directly with these scientists, because you're able to adapt and evolve what you're doing, I'm sure, to the kinds of questions that come up.
Yeah, absolutely.
Yeah.
All right.
They're very demanding people.
Go ahead, Oscar. Sorry.
No, they are very demanding people when it comes to presenting things, which is good. Which, I mean, in our case, it definitely shaped how everything looks, and the aesthetic choices are ours, but they have to conform to their requirements. So it's usually good to have intuitions about the data. Now, how do you have an intuition about the cosmic web? You read about it. You look at the sky. I don't know.
You sit under a tree, wait for an apple to fall on your head. I mean, who knows?
Well, going to nature is a big inspiration for me. Just seeing how everything in nature kind of relates to each other, and that there is universality in many processes that might look differently, like to the naked eye, but there is an underlying principle to all of these. And the whole slime mold works because there is a notion of optimal transport that guides the biology of the organism, but it also guides how gravity shapes the universe over time. And so you see these common denominators in these things.
Yeah, it's like a meta level of patterns. Yeah. All right, last chance, audience, for questions. If you've got a burning question, type it into the chat. Just some thank yous coming in. That's really nice. Okay, so I just want to thank everyone. This was a wonderful panel, such a cool range of work, and really appreciate everybody who is in the audience for taking time to come join us on Zoom. And I hope you will tune in for future Center for Computational Experience panels. There will be more. All right, thanks so much, everybody.
Thank you, everyone. Thanks for your questions.